In this video, we will discuss enhancing the efficiency of solar ponds as a topic in thermodynamics. You may or may not be familiar with solar ponds. What are solar ponds? Solar ponds are an example of a solar thermal energy system. When water is heated, its molecules speed up, bump around, and spread apart. The molecules now take up more space and the water is less dense. In ordinary ponds, heated water rises and loses its heat to the atmosphere. The goal of solar ponds is to trap this heat and not let it escape. This is achieved through the utilization of different layers of saline water, that is, water with dissolved salt. The more salt there is, the denser the water layer is. Typically, solar ponds are composed of 3 layers. The top zone, also known as the surface zone, interacts with the atmosphere and contains the least dense water. It may even contain fresh water. The middle layer is called the gradient zone and acts as a thermal diode as it directs the flow of heat from the top layer to the bottom layer. The bottom zone, which contains the densest water, is also known as the storage zone because this is where the heat is stored after the sun's radiation is absorbed. The heat stored at the bottom of the pond is insulated by cooler, less dense layers above. You may be wondering, what is advantageous about solar ponds? There are several practical uses and benefits of solar ponds. First of all, the cost to construct a solar pond is relatively low. Simple excavation and basic materials will not require outrageous amounts of funds. After construction, the ponds require minimal maintenance to operate. They can be used year-round, regardless of season or weather. The low costs associated with building, maintaining, and operating solar ponds is particularly attractive for rural, developing areas around the world. Another benefit of solar ponds is the fact that they are an alternative to fossil fuel technologies. They are safe for the environment as they do not produce pollutants or toxic byproducts. The heat energy that is stored at the bottom of the pond can be used for industrial production and other processes, agricultural uses, drying, distillation, and power generation. Let us look at some real-life examples of solar ponds. First, let us look at the largest operating solar pond in the world for electricity generation. The Beit Ha'arava solar pond operated until 1988 in Israel. It had an area of roughly 210,000 square meters, or approximately 52 acres. This pond provided an electrical output of 5 megawatts. That is enough output to power hundreds, potentially thousands of homes. In El Paso, Texas, there exists a much smaller pond, but it is still one of the largest solar ponds in the United States. It has an area of about 3,200 square meters, or approximately 8/10 of an acre. This pond powers 20% of the local operations of Bruce Foods Corporation. There exists a theoretical maximum efficiency of the thermodynamic cycle of solar ponds. This value can vary slightly depending on what assumptions are made about the system. Let's assume an air and surface zone temperature of 20 degrees Celsius or 68 degrees Fahrenheit. Next, let's assume that the water in the storage zone can reach a temperature of 90 degrees Celsius or 194 degrees Fahrenheit, slightly below boiling. Efficiency can be calculated as 1 minus the lower temperature divided by the higher temperature times 100%, where temperature is in Kelvin. Substituting our assumed temperature values, we get a maximum theoretical efficiency of 19.3%. While this may seem low, especially compared to other forms of energy production, it can be worthwhile because of the low cost and ease of implementation. If it is decided that a solar pond is to be implemented somewhere, achieving maximum efficiency based on current methods depends on the purpose and location of the pond. The right decision can provide the most efficient solar pond possible for its particular use. Several variations of solar ponds exist, and the geometry or dimensions of the pond is a major determining factor for classification. Let's look at a simple example. Suppose there are 2 solar ponds of different depths. one relatively deep and one relatively shallow. The deeper pond requires more time to heat the storage area, but once heated, it can store that heat for a longer period. Conversely, the shallower pond has the capability to heat more quickly, but it cannot store that heat as long. Both the time required for a solar pond to absorb heat and the amount of time it is able to store it can be understood as a function of its depth. This knowledge is vital to take into consideration when trying to optimize the efficiency of a solar pond, as requirements will vary in each separate case. Besides maximizing efficiency based on current methods, what design advancements can be made to increase the efficiency of solar ponds? The way heat energy is transferred from the solar pond is through devices called heat exchangers, which transfer heat from one medium to another. Traditionally, heat exchangers have been placed at the bottom of solar ponds, exclusively in the storage zone. This is what is shown in case 1. However, studies have been conducted to explore whether or not there are more efficient methods of heat extraction. Instead of placing heat exchangers on the bottom of a solar pond, what would happen if they were placed laterally, that is, on the inside walls of the storage zone? This is case 2. Case 3 considers the placement of heat exchangers on both the bottom of the pond and on the inside walls of the storage zone, which is effectively a combination of case 1 and case 2. Additionally, the idea of extracting heat from the gradient zone of a solar pond instead of, or in addition to, heat extraction from the bottom layer has also been explored. It has been found that, while heat extraction from the gradient layer alone will not be a more efficient method of heat extraction, it is possible to enhance the efficiency of a solar pond by extracting heat from the gradient zone in addition to the storage zone. Case 4 includes heat exchangers on the bottom of the pond and on the inside walls within the gradient zone. Case 5 includes no heat exchangers on the bottom of the pond, but features them laterally, on the inside walls of both the storage zone and gradient zone. Case 6 includes heat exchangers on the bottom of the pond and on the inside walls of both the storage zone and gradient zone. A study comparing the use of lateral and bottom heat exchangers, or a combination of the two, found that the efficiency of a pond increases when heat is removed from the lateral heat exchanger alone, as opposed to using only bottom heat exchangers or a combination of the two. Another study exploring the effects of heat extraction from the gradient zone found that extraction from the gradient zone in addition to the storage zone can increase the thermal efficiency of a solar pond by up to as much as 50%. Based on these two findings, the best locations for heat exchangers in a solar pond may be those of case 5, a combination of lateral heat exchangers within the storage zone and the gradient zone. Part of the maintenance of solar ponds includes replenishing water when it experiences evaporation. Can evaporation be limited? If so, it could increase the efficiency of the system in terms of maintenance and, more importantly, cost. One study compared two ponds. One pond had its surface covered with a thin layer of paraffin, a waxy substance. This layer was about a half a centimeter thick, or approximately 1/5 of an inch, and is represented by the purple line in the figure. The other pond had no paraffin layer. It was found that the paraffin layer could suppress evaporation. However, the trade-off is that the water in this pond did not reach as high of a temperature. The water in the storage zone of the uncovered pond reached a temperature of 76 degrees Celsius, or 169 degrees Fahrenheit. The pond with the paraffin layer reached a temperature in the storage zone of about 70 degrees Celsius, or 158 degrees Fahrenheit. Also, when it rained, the paraffin layer was swept away. This technique may be better for areas with warmer temperatures and less rainfall. The use of a layer to prevent evaporation can be effective, but it depends on the specific case. If it is found that this technique can be more cost efficient than simply replenishing water, it can be implemented. In conclusion, solar ponds can be an effective way to transfer the sun's heat into usable energy. How to maximize the efficiency of a solar pond depends greatly on the specific conditions of each case, including the pond's location and its purpose. Maximizing the efficiency of solar ponds is key in making them a viable option to store and use energy. Thanks for watching.